Okay, in this video, we're going to do the first part of section 12.5, which is about equations of lines and planes, and we're going to introduce the idea of a parametric representation for lines and planes in three-dimensional space. This first part, we're just going to focus on equation of lines, and then there'll be a second part video where we talk about planes. All right, so let's talk about lines in general. In 2 dimensions, when we have a line, so a line is an object that is straight, no curves, and it goes forever in both directions here. But in 2-dimensional space, we know that to define a line, we need to have the slope of the line, and then we have to have a single point that's on the line. So we have a point x0, y0, we have a slope m, and then we have a point slope form that we can use to build the equation of a line. Okay, so fairly straightforward in 2D. In 3D, we still have to have a point, so now it would be x0, y0, z0, and we still have to indicate something about the direction, but we can't just do that in terms of a slope or slopes. So instead, we define the direction the line goes with a vector. And the vector we use, we sometimes call it v, but we label typically its x, y, and z components as a, b, c. So there is some vector a, b, c, which you can think of as being at the origin, which is moving in the same direction as the line in 3-dimensional space, potentially translated to the origin. Okay, so we again have a way to specify a point on the line and then the direction of the line, except that the direction is specified with a vector instead of with a slope if we're in 3D. Okay, so there's actually 2 forms for specifying a line in 3D, and they're both related to the idea of defining a parameter. Okay, one of them is the vector equation form, and one of them is the parametric equation forms. So we'll talk about the vector form first. So imagine we had a line in 3D space. We have x, y, z, this blue line, and we want to come up with an equation that can represent it in some way that I could be able to move along this line and find all the points, the x, y, z values that are specifically on this blue line. Okay. All right, so what we can do is we start by defining 2 points on the line. One of them is going to be called P0, which is a known point on the line. Okay, so we'll have actually numbers here like 2, 5, 7 or something like that. And then we'll define a generic point P that has a generic x, y, z that is allowed to float and move along the line. Okay, so one fixed point and one movable point. And then we define position vectors to each of these points. So from the origin, a vector from the origin to P0, we're going to call that the vector R0. And then the position vector from the origin to the generic point P, X, Y, Z, we're just going to call that position vector R. Okay, and then we can define another vector that goes from the initial point, the known point, to the generic point. So we'll define that vector to be A. Okay. But we know from the geometry and the way vectors behave that the vector r here is the sum of the vectors r0 and a, because this is the orientation of the tips and tails here, is that if you take r0 and you add a to it, you get the sum vector r. So the vector r is equal to the vector r0 plus the vector a. Okay, but because a is parallel to the direction of the v vector, which we're using to define the direction of the vector, which could be any size, and that means this a vector is some scalar multiple of this v vector. It may be smaller, it may be larger, but we know that there's some scalar, which we're going to call t, that such that we could get the vector a by multiplying the direction vector v by this scalar multiplier t. And if we do that, then we can replace the a with t times v in this equation. And that means that the generic position vector r is the initial position vector r0 plus some constant times the velocity, or the v vector, the direction vector v. And this form is called the vector equation of the line. Okay? So what that allows us to do to be able to figure out points in the line is that we can vary this scalar constant t. So because we can vary it, we call it the parameter. Okay, and so we're defining something called a parametric form for a line. Okay, and varying that parameter will cause the arbitrary point to move along the line. So if we decide to set t equal to 0, then since this t is a 0, it'll be that the position vector is just equal to the r0 vector, the position where we already know the arbitrary point that we started with on the line. But if we allow t to vary, like at t equals 1, we will move to some other point in the line, p1. And if we allow the parameter t to be 2, then we'll move over here to t equals 2. And if we allow t to be negative, like -1, it would move on this direction in the line, over here to the position p -1. Right? So the idea is that if we allow this parameter t to sweep out any value from -infinity to +infinity, then that means we are moving along the entire length of the line. And this 0, this t equals 0 point, is fairly arbitrary. It just happens to be the t0, the t value, the parameter value, that will position us at the known point on the line that we used when we defined the line. Okay? So that's a parametric representation of a line, and varying t allows us to move along the line, either in positive or negative direction away from the arbitrary starting point. All right. So then if we take that vector equation and we just go ahead and write out the components again of these vectors. So the r vector is the generic x, y, z. The r0 position vector is x0, y0, z0. And the v vector is a, b, c. Then that means if you were to combine like terms here, right, the x, y, z vector would in fact be equal to the x components are x0 plus t times a, the y component is y0 plus t times b, and the z component is z0 plus t times c, right? So that means that the x component of any point on the line is equal to the initial known point plus the x component of the direction vector times the parameter t. And the y the same and the z the same. And if you want to cover the entire span of the line, you have to allow the parameter t to vary from -infinity to infinity. So when you write a line this way, it's called giving the parametric equations for the line, where you separated out the x, y, and z. And when you write it this way, the vector r equals the vector r0 plus t times the vector v. It's said to be the vector form of the equation of the line. Okay? All right, so a couple more terminology things. These ABC numbers, values that are the x, y, and z components of the direction vector that shows the direction the line is going, those are called the direction numbers. And if you take the parametric equations for x, y, and z, and you solve each of them for t, then that means since they're all equal, those expressions are equal to t, those expressions are equal to each other, right? So these particular expressions have the name symmetrical or symmetric equations. So there's a symmetric equations for each of the components, right? So x minus the initial x over the direction vector x is equal to y minus the initial y over the direction vector y, and so on. Now this could be problematic if the direction vector is 0 in any direction, like if b was 0, for example. But if that were true, then that means that the parametric form would be y equals y0 plus 0 times t. So then this equation is just y equals y0. Okay? All right. So let's actually look at a couple of examples to see how we use this, because we use these things very, very frequently in the rest of the course. So we'll just do some examples that play around with these ideas. The first one is find the equation of a line from the given point in the given director. So we want to find a vector equation and a parametric equation of a line that passes through this point and is parallel to this vector. All right, so what that means is that this point defines our initial vector. So our initial position vector, r0, is going to be the vector 3, -1, 4. And then our direction vector v is going to be -2, 1, 6, right? So essentially this is my a, my b, and my c, right? This is my x0, my y0, and my z0, okay? And then the way I'm going to do this, I like to do it this way by writing out the vector equation of the line. So the vector equation is r0 plus the parameter times v, okay? And that means that it's equal to 3, -1, 4 plus the parameter times -2, 1, 6, which means that it's equal to, in terms of the x component, it's going to be 3 plus -2 times t. So maybe I should write that as 3 minus 2t. That's the x component. And then -1 plus 1 times t, -1 plus t. And then 4 plus 6 times t, so 4 plus 6t, right? So this is the vector form. And in fact, since it asked us for the vector equation, this right here, well, actually, you could use this form. That would be okay, or you can expand it out to this form. Either of these are considered correct ways to express the vector form of the equation of the line. And if we want the parametric equations, we just go ahead and write out the x, y, and z separate. So that means that the x of any point on the line is 3 minus 2t, and the y is equal to negative 1 plus t, and the z is equal to 4 plus 6t. And regardless of which form we use, we also always have to specify what range the parameter can take. Since we're talking about the entire line, we have to say that t can be anything from negative infinity. Actually, I should not use an equal sign. From negative infinity to infinity. Some books will allow the equal, some not. I kind of like the idea that you can never get there because it's not a value. Right, so t goes from negative infinity to infinity, and then you can get the x, y, z of the points by plugging a particular value in here. So for example, this problem didn't ask for it, but let's say I wanted to find a few points that were on this line. So I could find different x, y, z values for given parameter values. So if I wanted to plug, for example, 0 in for the parameter t, this is a t, then my x would be 3 minus 2 times 0, which would be 3, right? And my y would be negative 1 plus 0 is negative 1. And my z would be 4 plus 6 times 0, which is 6, which happens to be the point that we were given, right? When the parameter is 0, we're right there. But if I wanted another point on the line, I could maybe make t equal to 1, in which case we would have 3 minus 2, which is 1. We would have negative 1 plus 1, which is 0. We would have 4 plus 6, which is 10. So this is another point that's on the line. And if I were to put, like negative 2 in there, then it would be 3 minus, and let's see, that would be minus minus, so plus 4, so that would be 7. And that would be negative 1 minus 2, so negative 3. And then this would be 4 minus 12, so that would be negative 8. Right, so all these points, these are 3 of the infinitely many points that are on this line in 3-dimensional space. And the way I access a different point is to just pick a different t value. So by varying t, I can span across the entire line. Right, but the main idea here is that we want to be able to write something either in vector form or parametric form and specify that t takes all possible values to generate all the points on the line. Okay, let's take a look at another example. So let's say that I wanted to find an equation that was for a line that passed through 2 given points. Okay, so if I wanted to do that, first of all, I'm going to have to figure out my initial value and my direction. Let's start with the direction. So my direction vector, it has to pass through these points. So what I could do is just take one point minus the other one, like maybe declare this is the end and this is the start, or whatever. It doesn't matter which direction I go here. Maybe I'll make this one the end and this the start. So if I did that, the x component would be 2 minus 6, and the y component would be 4 minus 1, and the z component would be 5 minus negative 3. Right, so my direction vector would be negative 4, 3, 8. And then I need to pick a point on the line to use as the initial point. It doesn't matter which one I use. Let's go ahead and use this one. Then that means the corresponding initial position vector would be 6, 1, negative 3. And then I would go through that same process. Here's my equation for a line. So it's going to be r is equal to the initial position vector plus the parameter, mixed in the parameter amount of the direction. And so that's going to be 6, 1, negative 3 plus t times the direction vector for negative 4, 3, 8. Right? And so, yeah, we could just say this is the expression for the vector. If I want to make it parametric, I could say x is equal to 6 minus 4t, y is equal to 1 plus 3t, z is equal to negative 3 plus 8t, and regardless of which form I'm using, I have to define that for the entire line, the parameter t has to go take every value from negative infinity to infinity. Okay? And note that because we arbitrarily want a particular direction here, you could scale this, you could use this point as the initial one instead of this one. There's a lot of different possible ways to write this, which would be correct, but this is one possible parameterization for this line. Okay, here's another example. Let's say we want to find an equation that given one point, and then it has to be related in some way to some other lines. Like let's say we want an equation of a line that passes through 2, 1, 0, but it has to be perpendicular to both these vectors. And these vectors are, let's see, 1, 1, 0, and also 0, 1, 1. So I need it to be perpendicular to both of those, but then also parallel to this. So let's make a kind of sketch what we're doing here. So we've got 1, 1, 0 is a vector that goes 1 in the x direction, 1 in the y direction, but not in the z direction. So that would be like that. And then 0, 1, 1 would be in the yz plane like that. So we need to be perpendicular to that, which means it needs to be the direction vector needs to be somewhere along this direction. And one way we can get a vector that is perpendicular to two others is if we do a cross product. So let's do this. Let's do the cross product of these two vectors first to get the direction vector, right? So let's just call this vector A, and let's call this vector B, and I'm going to say my direction vector V is going to be whatever I get when I take A cross B. So to do A cross B, I'll use my ijk thing here. That's supposed to be a vector. And I'll go 1, 1, 0, 0, 1, 1. And then I'll quickly make this vector. So the x component is the determinant here, which is going to be 1 times 1 minus 0 times 1. So 1 minus 0 would be 1. And then we have the negative of the determinant of these four numbers, which is 1 times 1 minus 0. So that's going to be also 1, but this time it's negative, right? And then the z component would be the determinant of these four numbers. So it'd be 1 times 1 minus 0, so 1 minus 0. So it looks like if I use 1, negative 1, 1, that's this vector, 1, negative 1, 1, I can use that for my v vector to make sure that my new line is perpendicular to those two lines. And then in order to make the equation of it, let me change colors. We're going to need to pick a point like 2, 1, 0 to be the r0 vector. So that'll be 2, 1, 0. And then we'll use the equation form here. R is the initial position vector plus t times the direction vector. And so that's going to be 2, 1, 0 plus the parameter times blending in some amount of motion along this direction. And so we could write that as 2 plus t for the x component, 1 minus t for the y component, and 0 plus t, so just t for the z component. So this would be the vector form. And we're again allowing t to go anywhere from negative infinity to infinity. Or we could separate those out as separate parametric equations. X is 2 plus t, y is 1 minus t, and z is equal to t, right? So this is the answer both in vector and parametric form. So the trick there was we had to get a direction vector by taking the cross product of two other vectors to force it to be perpendicular to those vectors. All right. All right, one more example before we move on to line segments instead of lines. So let's say we wanted to find, we just wanted to ask the question, is the line through these 2 points parallel to the line through these 2 points? Actually, I think for this, we don't need the techniques of this section. We can go back to previous sections. So let's actually do that. First of all, I could represent these as vectors. So let's take these first two, and maybe we call that vector 1. And so I'm just going to do x minus the difference between the x's and the y's. So maybe that would be negative 2 minus negative 4, 0 minus negative 6, and negative 3 minus 1. So that vector is 2, 6, negative 4, right? Then I have a second vector for this line here. using the same technique. 5 minus 10 for the x's, 3 minus 18 for the y's, and 14 minus 4 for the z's gives us -5, -15, and 10. Okay, and remember we said that one way to test for parallel, well, there's a couple ways we could do it. We could either do the cross product here and determine whether or not the cross product was 0, which would mean it'd be parallel. Or maybe even easier, let's just see if there's a scale factor that's the same, because if one is parallel to the other, it means you should be able to scale one up to make the other one. So I'm going to use that method. Looks like the numbers are bigger here. So let's figure out what the scale factor is to go from V1 to V2. So for x, it would be -5/2. For y, it would be -15/6. And for z, it would be 10/-4. And in fact, all of those simplify to -5/2. So in fact, the scale factor is the same for all the components. So these, the lines through these points, in fact, are parallel, because one is a scalar multiple of the other for all the components. Those are parallel. So we didn't really need the techniques from this section to do that. Okay, the last section we're going to talk about, or thing we're going to talk about before we wrap up for this part 1 video, is what if we don't need the entire line? What if I only need a line segment between 2 points on the line? Like say from point P0, x0, y0, z0, to another point P1, which is x1, y1, z1. Okay, so what that means is we don't need to have the parameter t go all the way from -infinity over here to +infinity. We just needed to cover the values from t = 0 to t = 1. Okay, so if you imagine that we made a vector that went between the 2 points, then that means that vector would have x component of x1 minus x0, and y component of y1 minus y0, and z component of z1 minus z0. And then if we want to use the vector form of the equation, it would be, we'd have an r0 equals, or an r equals an r0 plus a t times the direction vector. And so the r0 vector should be the starting point, v0, r0, which is x0, y0, z0, plus the parameter times the direction vector, but the direction vector is simply the difference in the x, y's, and z's. Right? And then if you were to multiply this all out, you're going to find that if you write this as a parametric equation, x is equal to 1 minus t times x0 plus t times x1. And the same for x, y, and z, just with y and z substituted. So if you kind of rewrite that back in this form, you get that r0 is 1 minus t times, or sorry, r, the generic r, is 1 minus the parameter t times r0 plus the parameter t times r1. But this time, t only goes from 0 to 1. Okay, and this kind of makes intuitive sense, right? If you have, let me change colors here a little bit. If you have the parameter t is set to 0 and you plug it in here, then you get 1 minus 0 times r0 plus 0 times r1, which means that r1 has no influence, and this is just 1 times r0. And that means that the position vector is positioned right at the initial point when t equals 0. Okay, but if you make the parameter 1, then what happens is you get 1 minus 1 times r0 plus 1 times r1. So that means you got 0 r0, and you have this equal to just r1. So when the parameter t is 1, you have slid over to this point. And as you smoothly move t from 0 to 1, the point smoothly moves along the line segment from the starting point to the end point. So we have a different form of the vector equation now. It is 1 minus t times r0 plus t times r1, but we only allow the t parameter to go from 0 to 1 to stay in between the 2 points. Okay? All right. That's going to be, we're going to use that so much that you're going to end up memorizing that actually. So might as well start getting ready to memorize it now. Let's go ahead and do one example, and then this will, I think, wrap up this will be the end of this video, and we'll do a separate video for planes. All right, find an equation if we have one point, and actually let's say we want to find a parametric equations for the line segment that goes from this point to this point. I think this doesn't apply. Yeah, so let's say we just want to find a parametric equation for the line segment that starts here and ends here. All right, so what we're going to do is we're going to say, all right, the direction vector is just going to go from here to here. So that's going to be 5 minus 10. Let me write it out. 5 minus 10. And the y will be 6 minus 3. And the x will be negative 3 minus 1. So that's going to be negative 5, 3, and negative 4. Okay. Yep. Is that right? Let's see. Yeah, okay. I'm not getting something that matches my key here, so just verifying something here. Oh, you know what? Let's not do it that way. That's why I was thinking I'm confusing myself here. So let me back up. I was going to do it in a way that is possible to do, but is actually even more work. The easiest way to do this is just to say my starting point is R0. So I'm going to use 10, 3, 1 for that. And then I want this segment to end at R1. So instead of explicitly writing out a direction vector, I'm just going to put a second position vector to the second point. And then I'm just going to use the definition of the equation, which is for a line segment, R is equal to 1 minus the parameter t times the initial point vector plus the parameter times the final points vector. So this would therefore be 1 minus t times the starting vector, 10, 3, 1, and then plus the parameter times the ending vector to blend that in as t increases. And so if I write this out, let's combine the x components together. It'll be 10 times 1 minus t. In fact, let me show all of this written out, although typically you'd kind of do more of this in your head. And then we would have 3 times 1 minus t over here. Then you'd have 1 times 1 minus t. That's this vector with this multiplied in. And then this is going to be 5 times t, and then 6 times t and negative 3 times t. And then if we combine the x's and the y's and the z's together, I'm just going to go ahead and multiply this out now. We're going to get 10 minus 10t, but plus 5t. That's the x component. The y component is 3 minus 3t plus 6t. And the z component is 1 minus t minus 3t. So combining like terms there, we get 10 minus 5t for the x component, 3 plus 3t for the y component, and 1 minus 4t for the z component. Okay, so this would be the vector equation version of this line segment between the 2 points. And I need to specify here that t is only going between 0 and 1 inclusive. That's really important to specify that so that we are talking about the line segment. Right? Or we can write this in parametric form as x equals t minus 5t, y equals 3 plus 3t, z equals 1 minus 4t with that same range of t's. All right, so that's where we're going to stop. We'll do a second video to cover the second half of this section, which is about how to make equations of planes.